Hello, everyone. I'm Li Weideng from the University of Electronic Science and Technology of China. Today, I'd like to share with you our paper, namely a semi-supervised framework for trajectory user linking. Firstly, I will present the study background. Trajectory user linking aims to identify users of anonymous trajectories, such as shown in the right figure. The owner of the upper three trajectories are unknown, and we want to link these trajectories to its owner. This problem has a wide range of applications, such as criminal investigation and personalized recommendation systems. Despite there have been lots of efforts devoted to this task, they usually have these problems. First, trajectory level information is not utilized. They mainly focus on many location level information, such as sequential patterns. Second, some of them simply treat this task as a general classification task. The inherent property of trajectories, such as spatial temporal information, is not fully explored. Besides, the results returned by the existing methods may be wrong, since they do not consider time span overlap constraint, which means that two trajectories with overlap time span cannot be linked to the same user, since one person cannot exist in different places at the same time. Moreover, they usually suffer from data sparsity problem, which needs plenty labeled data to train the model, while ignores the abundant unlabeled data. Before formally demonstrating the proposed model, we list three realistic hypotheses, which is guidance of the model construction. First hypothesis is based on repeatability. We hypothesize that the locations visited by a user is highly skewed, which means a user frequently visits the locations that he visited before. For specialty hypothesis, we hypothesize that the locations visited by a user are spatially local, which means a user prefers to visit a POI that is especially close to the location he visited before. For the last hypothesis, we hypothesize that the locations visited by a user are spatially and temporally local, which means a user prefers to periodically visit a POI that is close to the location he visited before. Next, I present the overview of the proposed framework. It consists of 5 components: trajectory level graph construction, trajectory relation modeling, location level sequential modeling, classification layer, and greedy trajectory user relinking. The main idea of trajectory level graph construction is based on 3 hypotheses stated before. In these constructions, we treat each trajectory as a node and link them with different hypotheses. For repeatability, we link 2 nodes if they share at least one same location. For specialty, we link 2 nodes if the distance between the locations in these trajectories are less than a predefined threshold. For spatial temporality, we link 2 nodes if these 2 trajectories satisfy spatial temporal proximity. Since these hypotheses depict different aspects of trajectory similarity, we can merge these edges to enrich the expressivity of the constructed graph. Specifically, we merge the repeatability graph with specialty graph and spatial temporality graph, respectively, to obtain 2 heterogeneous graphs. Although the trajectory level graphs have been constructed above, the contained information cannot be directly used. Thus, we have to vectorize the node in the graph. Considering the multiple relations in the graph, we simply adopt relational graph convolutional networks to deal with this situation. In spite of the trajectory level information is modeled into vectors, the details in the trajectories are ignored. Inspired by previous studies, we simply use LSTM to model the sequential patterns. Classification layer concatenates the inter and intro trajectory representations from the output of RGCN and LSTM to classify trajectories to the corresponding users. In the training phase, cross-entropy loss is used to train the model. To assure the compliance with the time span overlap constraint, we propose a greedy trajectory user relinking method, which is a post-process method. Specifically, after the linking probability of all trajectories are obtained, we sort all the probability values in decrease and loop them to allocate each trajectory to its owner if the looped trajectory does not conflict with the already linked trajectory of this user. We evaluate the performance of the proposed framework on 3 real-world datasets, Foursquare, Redkit, and Koala, compared with 6 competitors. Our framework is instantiated to 9 different models. Following previous studies, we adopt 4 widely used metrics to evaluate the performance of the model: ACC at K, macro P, macro R, and macro F1. We report ACC at K with K equals to 1 and 5. For all the metrics, the higher the value of these metrics, the better performance the model achieves. Here we present a part of overall. We present a part of overall. As through this table, we can observe that the proposed framework can always achieve the best performance. GNN-TUL outperforms the other baselines due to the exploration on high-order correlations among locations and the specialty of locations. TUL VOE that pushing unlabeled information through extra variational encoder is slightly worse than GNN-TUL. The variations of TUL have a similar performance on these datasets in all metrics. Although LCSS-KNN that leverage LCSS to determine the similarity between trajectories and then use KNN to classify trajectories performs the worst in most cases. It can obtain good results in terms of macro P on all datasets, which demonstrate that the repeatability information is helpful. Looking at the instances of our framework, we can see that instances that only consider repeatability achieve the worst, although the rest of instances have a similar performance. In example, all the components can outperform the others in most cases. We also study the effect of threshold in the graph construction. We have the following observations. Incorporating spatial information is helpful. The red line that uses repeatability and specialty outperforms the green line that only uses repeatability. The most suitable spatial and temporal factors varies a lot on different datasets. It will be better if they can be dynamically set. Keeping the heterogeneous of the trajectory level graph is important. If not, the performance will be dropped sharply, as shown in the purple line in these figures. Moreover, we also study the robustness of the model in terms of the number of the labeled data. Through this figure, we can see that the performance of GNN-TUL sharply drop with the decrease of the number of labeled data, and variations of TUL and TUL VE is rather stable. since it pre-trains pictures of locations using Word2 vector model. Moreover, the top 3 lines are the instances of our framework, which is also stable and always outperforms the others. This observation demonstrates that the proposed semi-supervised model is useful. We conclude our paper as follows. We design 3 heterogeneous graphs and we design 3 homogeneous graphs and 2 heterogeneous graphs for modeling the inter-trajectory relationship for trajectory user linking problem. We propose a greedy trajectory user relinking method to assure the compliance with the time span overlap constraint. We conduct extensive experiments on 3 publicly available datasets, comparing with 6 representative competitors. So that's all. Thanks for your attention.